All right, we're going to talk about exponents and logarithms. You guys are being recorded, by the way. So exponential and logarithmic functions. The stuff that we learned in the polynomial functions, cubics and quartics and all that stuff, those are fine, those are nice, but they're rather gimmicks when it comes to actually using models of mathematics to map out real phenomena, right? I mean, we're all fairly familiar about exponential functions in the light of, well, COVID-19, right? As of time, COVID appeared in China, Wuhan, China, and they started having some cases and whatever, and they started to really increase a little bit, and then it went like this, right? And we were all freaked out because the amount of virus cases that we have was growing at an exponential rate. And an exponential rate can be a very serious thing. If we look at numbers and we double them, we go from 1 to 2 to 4 to 8 to 16 to 32 and 64 and 128 and 256 and 512, we can see that these numbers go up very, very quickly, right? Because then you're up to 1024 and then 2048, and they start doubling really, really, really fast. And this is the scary thing about it's not the scary thing, but it's the idea behind these exponential functions. The way COVID has been transmitted, we've been using a function where we have y is equal a to basically 1.2. If we have it to the 1 power, it's just not going to increase. It's going to stay the same. If it's the second power, then it's going to double, right? And then this a factors has to do with your degree of transmission. Getting this number down to 1 is where the science in what we've been trying to do by wearing face masks and social distancing and sanitizing our hands. We're really, really, really targeting this number to try to get it down. Now, when they're talking about flattening the curve, when they had something like this is actually a calculus integral from an exponential function. Our exponential function as things increase looks like this, but then you also have the amount of people that can be infected that goes down like this. And between these two graphs, you're going to get this one. By lowering that transmission rate, you're going to squish that hump down. And the idea is that there's a certain line there that's the ability of hospitals to take care of their patients. But anyway, let's think about a frog pond. And they start with a little lily pad over here, and then it doubles to another lily pad, and then that doubles to 4 lily pads, and then that doubles to 8 lily pads. And we can see that slowly the amount of lily pads growing in the frog pond is going to increase, right? But what is really striking is that on the last day, the pond is full, right? The day before that, the pond is half open. And the day before that, it's 3/4 open. And the day before that, it's 7/8 open. So it gets really, really full, really, really quick at the very last stages of it. And this is why the pandemic has been so scary, is because science has been like, whoa, what's going on right here? Knowing that this part is coming, right? Now, right now, I just looked at a graph of where COVID is, and it's gone up like this. And it's got this seesaw approach. And it kind of meshes with what people's perceptions are, is they get to about here, and they start freaking out, and then it goes down, and they get tired of social distancing, and they want to engage with each other, and so it goes back up, and then they get tired of it, and goes back up, and so it tends to be this like cyclical thing. When we had the Spanish flu in, I think, 1916, it basically had the same thing, and it went way off the chart. We had this little hump, and then it went way up. The mathematics behind this are relatively straightforward. You've got f of x is equal to a to the x. A is, we're going to say, is some value where it's greater than 0. And we're also going to say it's not equal to 1 either, because that's not very interesting either. 1 squared, 1 to the third, 1 to the fourth, that's all equal to 1 anyway. All of these graphs are exponential functions, and they all look something like this. They always cross the y-axis at 1, unless there's some sort of vertical or horizontal shift in it, okay? Now, you can have, different flavors of it, where you look at, if you can switch it over the y-axis, you get something like this, switch it over the x-axis, and then vice versa. You can always get different flavors of that exponential function. But as long as there's no vertical or horizontal shifts, it's never going to cross the x-axis, right? You're either going to have all positive values or all negative values as your output. Now, another type of logarithmic feature we're going to look at is something called the logistic curve. And this one is actually very super important. It starts off like this and tapers off. And there's something called here, a value of C called the carrying capacity. And that carrying capacity is the upper limit of the output of this function. Now, this function is very complicated, so I'm only going to ask you to kind of put some values in. But there's some nice features for this as well. You have this point right here in the very center, where it switches from being, concave up to concave down. That's known as the tipping point. And that tipping point is very, very critical. We talk about tipping points in populations or climate change, things of that nature, looking at where that point and being able to move that point where we're always increasing, right? But past the tipping point, our rate of increase is starting to get slower. It's starting to decrease. If we look at human population models in the world today, we're right about here. We're right just past the tipping point. We passed it in about the early 2000s, okay? But that's for the entire world. If you look at population in certain countries in Africa, they look like this. They keep going up. If you look at population models for like the Netherlands, where most couples don't have 2 children. The amount of children they have is less than 2. So their model starts to look like this, right? And then there's a lot of other countries that are somewhere in between. The interesting factor that controls this curve, they found out, is the education of women. The more that women are educated, the more likely that you're going to have a population where you're going to decrease the amount of population, which I find very, very interesting. We also have logarithmic curves. And logarithmic curves are the inverses for exponential curves. And they all look like this. So where you have an exponential curve will look something like this, right? The logarithmic curve is going to be a reflection of that exponential across y equals x. Logarithms are important too. They increase without bound, meaning that this part here, this very end, is always going to go up to infinity. Also, the domain is such that all the numbers have to be greater than 0. You can't take the logarithm of a negative number, okay? Now, you can reflect it across the x, across the y, do some certain things like that, but there are some rules with logarithms as well. And just like for the exponential where it crosses at 1 here, the logarithm also crosses at 1 over here. Now, logarithms have many applications, but we used to have something called the slide rule. And that slide rule was before the dawn of the calculator, and they would multiply large numbers together. So if you had, it was 5,286, and you wanted to multiply that by 489, right? Doing that by hand takes time. But what scientists would do is they would say, okay, we're going to write this as 10 to the 3.6 maybe. We're going to write this as 10 to the 2.7. Now, when you multiply numbers that have the same base. For example, if I did x squared times x cubed, what do we actually do to those exponents? We just add them, right? So what the logarithm did is that we were allowed to say, okay, we can change these into 10 to some power, and then we can add those powers together, and then change that back to a different number. And so you can do advanced multiplication for big numbers really quickly by changing them to their logarithms. And this was the basis for the slide rule. Okay? Now, things like pH. If you have a pH of, well, we have a scale, and 7 is right in the middle, and that's your concentration of, I think it's hydronium atoms or something, or I think it's H30 plus or something. Some books I think use H plus or whatever. But this scale is weird because a pH of 8 is 10 times more basic than 7, right? But a pH of 9 is 100 times more basic than 7. So this scale is actually crushed down quite a bit. It's a logarithmic scale, okay? Same thing with like the Richter scale and earthquakes as well, right? A magnitude 9 earthquake is 10 times worse than a magnitude 8, but a magnitude 9 earthquake is 100 times worse than magnitude 7. So as much as like you guys are getting some math and learning how to do math, I think especially these two sections with exponential and logarithmic functions, you actually gain a lot of math literacy and like how that kind of information can allow you to make good decisions. Any questions?